Welcome to the AI Research Roundup. I'm your host, Alex. Today is May 8th, 2025. We're looking at an ICLR conference paper, LaMPlace, Learning to Optimize Cross-Stage Metrics in Macro Placement, out a few months. This paper tackles chip design's macro placement, that's positioning large circuit blocks. Current AI often optimizes simpler surrogate metrics, like wire length, not the crucial cross-stage metrics that define final quality. These include timing performance, like worst negative slack, or WNS, and total negative slack, or TNS, showing if a chip meets speed goals. Evaluating these is slow, so LaMPlace aims to predict and optimize them efficiently. Okay, so this first figure really sets the stage. It shows the typical electronic design automation, or EDA, workflow. That's the overall process for designing computer chips. You can see the different stages like macro placement, cell placement, and routing. Traditionally, methods optimize for simpler metrics at each stage, like wire length. But the key takeaway here is that LaMPlace, as shown, aims directly for the final power, performance, and area, or PPA. These are measures of the chip's final quality, and also those critical timing metrics, worst negative slack and total negative slack, not just intermediate ones. Okay, this figure really lays out the LaMPlace method. Part A details training the predictor. Using a netlist, the chip's blueprint, a graph neural network, an AI good with connected data learns to predict final chip quality metrics. It does this by determining L flows for a special mathematical model based on past designs. Next, Part B shows this predictor creating an L mask, a heat map, guiding a greedy algorithm for fast macro placement. Finally, Part C is a performance chart, visually confirming LaMPlace achieves better results on key design metrics. Alright, building on how LaMPlace works, this table then details its performance against other methods like DreamPlace and ChipFormer. It compares them across various chip designs, looking at metrics like half-perimeter wire length, or HPWL. That's a common way to estimate the total length of wires needed, and congestion, which tells us how crowded the wiring paths are. Crucially, for the timing metrics, total negative slack and worst negative slack, LaMPlace consistently shows better results, meaning faster chips. The rank rows further confirm LaMPlace's strong performance across the board, really backing up its effectiveness. Okay, so to dig a bit deeper into why LaMPlace is effective, this figure shows a correlation analysis. Part A just illustrates how the various chip metrics, like half-perimeter wire length, and the timing measures, total negative slack and worst negative slack, interrelate. The key part, B, compares how well LaMPlace's predictions connect with these final outcomes. A correlation coefficient, simply put, measures this connection strength. And we see LaMPlace's predicted timing values, marked P, and its overall pred output, align much better with actual final timing performance than traditional surrogates like MHPWL. This strongly suggests LaMPlace is truly optimizing for what matters in the end. So, to really see how this L mask guides the actual placement, this figure provides a clear illustration. Part A displays the L mask, that heat map we talked about, where blue spots highlight the most promising locations for placing a circuit block. Then, Part B shows a legalization mask. This is essentially a filter that makes sure macros don't physically overlap. Finally, Part C and D demonstrate the step-by-step placement, using that L mask to select the optimal, non-overlapping position for the next macro, shown in blue. It's a neat visual of the system at work. Following that detailed placement process, this next figure gives us a visual comparison of the final chip layouts. We're looking at post-routing results. That's after all the wires are laid out for a specific benchmark, comparing wire mask EA, ChipFormer, DreamPlace, and LaMPlace. The red areas you see highlight overflow areas. These are essentially spots where the wiring has become too congested, and it's quite evident that LaMPlace, shown in panel D, has significantly less red, indicating much better routing and reduced congestion compared to the other methods. This really drives home its practical benefits. Alright, and to put some hard numbers to those visual improvements, this table shows the post-routing PPA results. That's power, performance, and area. Key chip design goals. for a specific test case called Super Blue 4 feet. We see comparisons for routed wire length, those congestion metrics again, like routed horizontal and vertical overflow, and the crucial timing figures, worst negative slack and total negative slack, along with number of via poly, which relates to connection complexity. LaMPlace really shines in reducing wire length and overflow, and also achieves the best total negative slack and number of via poly. While ChipFormer is slightly better on worst negative slack for this specific design, LaMPlace's strong showing across most metrics here, especially the significantly lower overflow, really underscores its advantages. So these strong results really highlight the core idea here. LaMPlace effectively tackles that tricky problem of optimizing for final chip quality, those crucial cross-stage metrics like timing, by first training a smart predictor offline. This predictor uses a graph neural network, an AI model that's particularly good at understanding relationships and patterns in data structured as a network, like the connections between components on a chip, to generate that L mask we saw guiding the placement. This leads to some really impressive gains, especially in chip timing. Thanks for tuning in to the AI Research Roundup. I'm Alex, and I'll catch you next time.